With that, I'm very pleased to introduce our speaker for our main presentation. The presentation is Designing Autonomous AI Agents for Next Generation Scientific Workflows. This is one of the hottest topics in computational science right now, and I'm very pleased to introduce Kyle Chard, Research Associate Professor at the University of Chicago and an Adjunct Professor Researcher at Argonne National Lab. Kyle, thanks for joining us today.
Thank you, Jay, and thank you so much for the invitation. What an amazing community that you all have here. So I'm very pleased to be here. I'm just going to start presenting my screen. And Mary, Jay, does that look okay?
Looks great.
Okay, awesome. Well, I'll get started. Thanks again. I saw many of you say hello from wherever you are in the world. It's amazing to see such a worldwide community and to see people awake in the middle of the night attending this talk. So I'm going to give an overview today about how we're thinking here at the University of Chicago and Argonne more generally about designing autonomous AI agents with a real focus on scientific workflows. So my background is very much distributed systems, scientific computing, and I'm going to talk a lot about some of the challenges of building these agentic systems to power the next generation of science. So let me start with a little story. So I think it's been well known that humans have long been the bottleneck around the scientific method. So one really good example, I think, is Kepler, who's obviously one of the most well-known astronomers in history. And when people talk about Kepler, they talk a lot about his laws of planetary motion. So the first law being that every planet is essentially orbiting the sun in an ellipse. So how did he go about making this discovery, right? So he was handed a pretty amazing data set in 1605, and he took 4 years basically going through the scientific process, proposing a hypothesis, analyzing that data, and recycling, right? Going thousands and thousands of times trying to work out this ellipse, this pattern that he was seeing. So effectively what he was doing was following the scientific method. It wasn't a case of him being personally slow. It's just that every iteration of this loop required himself to be able to run this. And for hundreds of years, this bottleneck really hasn't changed, right? We've made scientific instruments that can acquire data and take images at higher resolution than we previously could. We've made massive supercomputers that can run ridiculously large scientific calculations to determine structures of materials, et cetera, et cetera. We've built enormous data sets that we use for powering these new AI models, and we have a series of automation softwares that enable us to automate scientific processes at some degree. But fundamentally, the scientific process has really been constrained by the human. And so this is where the promise of AI agents come in, right? That the agent is a system that can run aspects or the entirety of this loop autonomously, and that's what we're going to focus on today. So let me start with a pretty quick definition of what an agent is, and then we'll get into some more specifics to break this down. So very simply, an agent is a persistent, stateful process that acts on behalf of a user or a system. So there's sort of four important characteristics that we focus on here. First is that the agent can sense or observe the environment around it. It can take inputs, can observe events, right, and it can respond to them. Secondly, it can plan. It can make decisions on which actions to perform using some sort of policy. Traditionally, these agent policies were more rule-based. In recent times, these policies are, of course, driven by language reasoning models, et cetera. These agents, importantly, have the ability to act on their environment around them, perhaps by executing tools, perhaps by communicating with other agents, perhaps by interacting with a human. And these agents are able to learn based on their experiences. They update their state. They adapt over time. They may fine-tune a model. They may record their experiences. And so we like to think of an agent really as a capable scientific colleague that can reason, act, and coordinate autonomously towards some sort of objective. So as I alluded to, agents really are not a new concept. Agents have been in the literature for many decades now. So why is there so much excitement about agents at the moment? And you can see here a plot of the Google search trends, which is often a great proxy for sort of what the hot topics are in the world. And you see on the top there language models sort of growing from the early 2020s through to where they are now. And you see sort of in the mid 2024 range that agents really starts taking off. And so the real reason that agents, I think, have become so popular now is that their capabilities in the mid 2024 range really exceeded that of what expert humans could do. We had these advanced reasoning capabilities embedded within these models that could actually make really informed decisions. Another way of looking at that is to look at the actual capabilities of language models themselves. So many of you have probably heard of the graduate level Google Proof Q&A test, which I think is a really wonderful idea. And the idea here is that a group of researchers assembled a set of really specialized domain-specific questions that were very difficult to answer even with Google at your fingertips, right? Being able to search for the world's information, being able to answer these questions. And so you can see a couple of lines on this plot. So you can see a line towards the bottom there at 34%. So this is basically the question, the percentage of questions that a human is able to answer correctly, a human with a PhD, but answering questions outside of their domain science. So this would be me as a computer scientist trying to answer questions in, say, biology or materials science. And so with Google, I could hit about 34% of these questions. The line at the top you see is a human PhD in their field. So again, me as a computer scientist, if I was asked questions about computer scientists, this test, I would roughly get about 81%, right? So that tells you about the level of complexity with these questions. In the plot, you can see points there for each of the language model releases. You can see the GPT releases there, right, from GPT 3, 4, 01, and 03. And you can see the inflection point there with the later half of this graph in 2024. Basically, we're seeing the capabilities of these language models go from an expert outside their specialty to actually being able to exceed the abilities of an expert within their specialty. And this is the core of what's driven agentic systems, right? These capabilities are now made this autonomy truly practical and possible. So when we think about language models, there is still a significant gap. So this is a little vignette, a little example of interactions with a language model showing you what's missing. And what's missing really is the ability for these language models to act in the world around them. Okay, so they serve as these enormous references, this access to an enormous corpus of information, but by themselves, they're not really designed to be able to act in the world. So in this example, what we're doing here is we're asking a language model how much energy is going to be released in the combustion of methane. And we suggest in the question that, well, you should use the GFN2 XTB method at 400 Kelvin, okay? So let's prompt a model with this question. We did this a couple of months ago. Things have changed a little because the big providers are adding more and more capabilities to the models. But when we ran this is what happened, right? So it said to actually calculate the enthalpy change using GFN2 XTB at 400 Kelvin, I would need to run the XTB software package on molecular structures for methane, oxygen, carbon dioxide, and water, and obtain the thermal corrections at 400 Kelvin. Unfortunately, I don't have the ability to execute XTB calculations directly, of course, right? It has no ability to act in the world. So what would happen then if we take away the instruction to use this GFN2 XTB method, and we just say, just calculate this computation for us. Look at your extensive information and tell us what you think the answer is. ChatGPT will respond here, and it tells me that the reaction is approximately negative 8.3 electron volts, which is unfortunately incorrect. It's what many people would refer to as a hallucination. It's probably pulling some slightly incorrect information about some of these compounds. So what we're missing, as I keep saying here, is this ability for this language model to actually act in the world around it. And so what we can do, and this is what some researchers at Argonne did, Murat, Kelsey, and others, built an agentic framework, in this case called ChemGraph. And you can see in this example, this ChemGraph agentic framework was driven by a language model, but enriched with a set of capabilities to actually run molecular simulations. So in this case, they're using a simulation, a tool suite called the Atomic Simulation Environment, ASE, and XTB, which is the simulation package for running these GFN XTB simulations. And you can see, if this is big enough for you can see basically what's happening. We're decomposing this instruction. We're saying, well, to actually work this out, we first need to, we ultimately want to run an XTB simulation. In order to be able to run an XTB simulation, we need to have these molecules converted to SMILES strings, converted to their atom structures, and then fed into the XTB tool, and then the calculations of the individual energies being computed. And you can see the path there of this ChemGraph framework calling these series of tools, and the result being negative 12.51 electron volts, which happens to be the correct answer. So what I've described here is really what this agentic world is bringing us. It's basically enriching these very, very sophisticated language reasoning models with capabilities to actually act on the world around them. And so as a sort of summary of the distinction here of moving from a language model to an agent, essentially a language model is sitting there waiting to be prompted. It's answering directly the queries that are given it to us. It typically doesn't have a large amount of memory between these queries, and a human is ultimately driving all of those steps. So I think of language models as sort of an extensive reference. It provides access to the world's information in a very intuitive and easy to access manner. In contrast, an agent is more autonomous. A human is setting an objective of some form. That agent then is trying to achieve that objective. It's monitoring the environment around us. It's making decisions. It's planning, and it's acting across many steps. And it's remembering and adapting and iterating on those processes. And you can already start to see, when you think about that scientific method I introduced at the beginning, you can start to see how an agent could start to perform many of those steps in the scientific method. And I think of an agent as sort of a very capable colleague that's able to work all day, work while you sleep, and you're able to come back and see the results that have been generated. So there are many scientific tasks that I think would benefit from agents, and not just me. This is many other people have proposed such things, right? There's a lot of mundane, repetitive activities that scientists are performing. There's a lot of challenges now that are facing science in terms of even simple things like keeping up with the enormous body of literature that's published every day. It's completely infeasible for a scientist now to track all the publications in their area and be able to ingest them and understand them and relate them to their work. It's impossible generally now for scientists to operate at the level of these supercomputers. Using 100,000 GPUs is a very, very challenging task, and to think through the types of simulations, be able to consolidate that, observe it, and understand what's actually being done. So I think there's many opportunities for us as humans to outsource many of these tasks to capable agents, capable colleagues that can perform these actions for us, much as a PhD student or a postdoc does in current everyday life. So examples of things where agents are already being widely used: monitoring and synthesizing literature, adaptive experimental design and scheduling, cleaning and harmonizing data sets, managing HPC jobs and simulation workflows, and even driving robotic lab instruments and self-driving laboratories. So that's sort of a summary of where we are in thinking about agents. What I'm going to talk about now is a couple of concrete examples of where we're seeing agentic systems being deployed and used. I'm very fortunate to have a role in at Argonne National Lab and as part of the Department of Energy's Genesis mission. So if you're not familiar with this, this is a national effort to build world-leading AI infrastructure and capabilities, and then to apply these new capabilities to the most pressing science and technology challenges in the world. So DOE is blessed with an enormous set of data that's been curated and collected over many years in very specialized domains, from materials science to biology, energy science, etc. Has an extensive workforce of talented researchers and scientists who are very AI capable, and has some of the fastest supercomputers in the world. So really, three of the core requirements to really innovate in AI and science. As part of the Genesis mission, I'm part of a group called the Common Agentic Framework, and we are working across many of the model teams funded in Genesis to support and help them with their agentic deployments. Over the last year, we've seen literally dozens and dozens of agentic systems being built and deployed by scientists in domains spanning materials discovery to astrophysics to plant science to even HPC code development, et cetera, et cetera. And I'm going to talk about a couple of examples of agentic systems that we've seen be developed, both on the DOE side and also more broadly across NSF and other science domains. And I apologize for the US-centric acronyms there. I realize that there's an international audience. So DOE is the US Department of Energy, NSF is the National Science Foundation, but several of these examples are much more broad than specific US agencies. So let me start with a pretty common type of analysis that's done by scientists around the world. In this case, framed around materials discovery, but similar types of processes are applied to other large search spaces. So in this case, what scientists want to do is they want to discover what we call metal organic frameworks that have desirable capabilities. In this case, perhaps capturing methane, capturing carbon, etc. And so a metal organic framework is a really interesting material that combines ligands, these organic molecules, with inorganic metals, these nodes, and essentially glues them together in what look like sponges. And these sponges are porous structures that are really good at absorbing and storing gases. The problem for our colleagues is that the search space of potential MOFs that would be useful is enormous, perhaps infinite, because there's many ways that these ligands and nodes can be developed and assembled in different geometric combinations. And so what we want to do is think about, well, how can we efficiently discover MOFs that have desirable properties for these target applications? So what a set of researchers at Argonne National Laboratory did is they built a framework called MOFA. And the idea of MOFA is to basically automate this discovery process using a series of agents to do various actions or activities within that overarching system. So they have I'll walk through each of these components. They have an AI agent that basically drives this entire workflow. So they've built a specialized model on their enormous collections of data. This model can generate ligands that are potentially useful for assembling MOF structures. They then combine this generative model with a series of computational agents that themselves are independent entities operating in computational environments to perform specific roles under the guise of this overarching objective. The overarching objective being discover MOFs that are good at X. And so we have agents there that are responsible for assembling MOF structures. We have agents that are responsible for validating that those structures are physically reasonable. We have agents that are responsible for optimizing the structures, and then agents that are ultimately responsible for estimating characteristics of that structure. We have another agent that's responsible for storing, harmonizing that data and making it accessible such that we can retrain that specialized model to be better at producing good ligands. And the interesting thing, asterisk on this one, is that you can also combine other types of agents into this system. We haven't done this, the researchers have not done this, but we have large automated laboratories here at Argonne that can synthesize, conduct experiments for us. So you could imagine in the future being able to add an embodied agent that connects with a self-driving laboratory that could actually augment this process even further. So these researchers basically took this structure for how they wanted their agentic system to be implemented, and then they deployed this agentic implementation across various computing resources at Argonne and more generally across the US. So they took several of these agents and deployed them on the Aurora supercomputer. These agents that were able to generate the ligands, validate the MOF structures. These were able to exploit the many tens of thousands of Intel GPUs available on the Aurora supercomputer. The optimization phase, this was really designed to work on an NVIDIA GPU. So they deployed the optimizer agent on the Polaris supercomputer and ran optimization there. And then the other agents, the assembler, the estimator, and the knowledge agent, they are much lighter agents that don't really need much by way of computational capacity. So they deployed them on the Chameleon cloud environment such that they were always accessible and could drive these generation, optimization phases, etc. So interestingly then that they then looked at this, so they set the objective, go and discover some MOFs, gave it an allocation on these machines and set the agentic system off. And you can see here an example from top to bottom of trying to log what's actually happened in this agentic system. So you can see on the top each of the phases, each of the agents when it's actually executing, because these agents are smart enough to know they shouldn't be executing when they don't have any work to do. You can see on the bottom the number of tasks that they're running. Of course, they're only doing tasks when they've got things to do. And on the very bottom pane, you can see how many computational resources are allocated. Of course, that mirrors the tasks that need to be executed. And you can see various phases of what's happening here in the agentic system over time. Those very blocky resource allocations are, of course, an artifact of many HPC systems have limited durations that we can run jobs. So the agents were losing their jobs and then smart enough again to resubmit jobs for execution when they had worker waiting. So we sat down with these researchers after they'd been working on this for a while and tried to understand, well, so you had the option to potentially implement this with a more linear sort of traditional workflow. You implemented it with an agentic approach. What were your experiences? What did you find useful? What did you find not so useful? I'll focus here on the useful. We can discuss later the less useful. The less useful being things like the autonomy, the observability, the diagnosability, etc. So one of the reasons they gave us was the autonomy was wonderful. It was outsourcing to each of these agents the responsibility for provisioning resources and running computations according to the higher level objective was great. They didn't have to micromanage any of these things. The placement was a real benefit because they were able to deploy these agents in different places when they found that various aspects required specific types of hardware. They liked the separation of concerns. So this is really a sort of modular software engineering type property, right? That the resource acquisition and scaling could be handled independently based on what each agent was doing. They like the loose coupling, so being able to swap agents out for different types of simulations, or potentially in the future integrate, say, a self-driving laboratory. That's what SDL stands for. And then a big asterisk here for a very future. They often pondered, and a lot of people we talk to talk about this desire to be able to share their agents with other people. A lot of these research groups have developed agents that they believe would not just be useful for the types of science they're doing, but would be useful for other types of science. So that's one really concrete example of where agentic systems have helped this group of materials scientists. Now for something completely different. So this is a really wonderful example from Oak Ridge National Laboratory. So this is the Advanced Plant Phenotyping Laboratory. I had no idea such a thing existed until we started hearing about their agentic system. And so this is essentially a robot lab for plants. So they have essentially conveyor belts where they grow these plants, and then they slide them along conveyor belts and take measurements of the growth of the plant. So what they'd like to understand is the characteristics that lead to good growth, right? So they associate the phenotype with the characteristics of how that plant was fed, what environment it was growing in, et cetera. So hopefully they can obtain, I guess, biologically useful insights. And so what does this look like, right? So they have this nice robot equipment that's sliding these plants through these conveyor belts all the time. They're producing enormous amounts of data. They then are using AI methods because it's not tractable for a human to actually be able to analyze all of this data coming off this roboticized plant laboratory. So one example of AI, they use AI methods to basically calculate these spectral traits. And what they do is they take these images that are taken every day, every night, etc. They segment them to remove the background. They calculate the morphology of the plant. They compute various spectral traits, and then they feed that into analysis algorithms that can try and compute sort of charts of growth over time and start to map back to phenotype characteristics. How is this actually implemented? So this is work that I'm not involved in. This is work done primarily by Daniel Rosendo and Renan Souza, as well as the much broader Apple team, which is part of the Genesis project. And what they've done is they've implemented a system in which they've deployed agents on a Kubernetes cluster running in the cloud. These agents are essentially responsible for managing the influx of data and also providing an interface to users, a chat-like interface where users or scientists can ask questions of the data that's being calculated, right? Like, tell me about what characteristics have been really led to really very desirable growth conditions, or perhaps the opposite. These agents in the cloud are actually driving pretty significant scientific workflows running on the Frontier supercomputer at Oak Ridge. And so these computations are using things like vision transformers to actually run these computations, all driven in an automated fashion when data arrives, an agent saying, well, I've got this new data, we need to start running processing, or in response to queries from users. And then for a completely different example, which is another one I love, I'm trying to give you as broad of a spectrum set of examples as possible to try and capture some of the true capabilities of these agentic systems. The third example is some really wonderful work by a fellow by the name of Isaias Fernandez. He's works for the World Health Organization in Africa. And he has this system called the Preparedness Data Exchange. They have a really interesting requirement that they're very focused on data sovereignty. So they would like all of their data, all of their computation to remain within the nations of Africa. And what they've done is they've built this really interesting system that can basically take streams of information from various sources, streams from public health officials, streams from national departments that are producing data, streams from other philanthropic organizations, streams from news media, even streams from weather sources. And what they try to do is merge all this data together in ways that they can produce alerts. They can try and identify characteristics or situations that may lead to potential viral outbreaks, etc. And so what they've done is they've used an agentic system here where they've deployed agents that are using various language models to basically make the first run of decision-making on stream. So the agent interprets the stream information that comes into it, makes decisions, maybe checks another stream and combines that information together, but ultimately will alert a particular type of person, maybe a public health worker, maybe a government entity, of a particular scenario arising. And then that individual is able to actually come into this engine and be able to inspect that data individually. So here you're seeing the ability for a sovereign agent to be deployed within the African region in response to streams of information that are being processed. I should say I don't have a ton of time to talk about other agents, but as part of the Genesis mission, one of the things the Common Agentic Framework team is focused on is trying to document the types of agentic systems that are being deployed. So you can have a look at this website, and every week or so, there should be a new agentic system described. Think of it as like a short, easy to digest blog that tells you about the types of agentic systems being used in the Department of Energy space. So that's sort of a highlight reel of some of the examples of scientific applications that are leveraging agentic systems for various purposes. So now what I wanted to focus on is, well, how do we go about implementing agentic systems for science, and what are some of the really outstanding challenges that we as a community need to think about addressing? And I should say again, I come very much from the systems perspective, so I'm thinking a lot about some of the challenges of deploying these agentic systems at scale for scientific scenarios. So if you're just getting started, there are so many wonderful agentic frameworks that you can use. They all provide sort of subtly different capabilities that are aligned for slightly different use cases. So I suggest having a look at several of them, comparing and contrasting the interfaces, the capabilities, the interoperability with one another to try and match with your type of example. But many common ones that we see a lot of are things like LangChain and LangGraph. Obviously, the Google suite of agentic frameworks like the Agent Development Kit and many others, Small Agents, Pydantic AI, et cetera, and of course, Claude is a central driver. So one thing I think we've learned over the last year or so of working with these scientific agentic systems is that really not all agentic systems look the same. There's really quite at least from our experience, we see three main patterns of the types of agentic systems that are being deployed. And these agentic systems are being implemented with different frameworks. They all fit in different buckets. So this may be a slight oversimplification, but at least we'll get you thinking about the types of architecture you might imagine. So the first is very much a coordinator or orchestrator type model where an agent has sort of one brain and it has a set of tools at its disposal. So much like the ChemGraph example I talked about at the beginning, we have these capabilities to run these simulations. The agent is the brain behind interpreting an objective, running the tools, bringing the results back. There's more of a workflow chain pipeline type approach where we have a set of specialized agents that are connected together in some sort of directed acyclic graph. There's a control flow based orchestration model that's overlaid on top of these agents, perhaps with some tool calls occurring in there as well. And often these are defined a priori as a structured sort of representation of what that system should look like. And then there's the more federated model where agents are deployed more autonomously and independently and are coordinating their actions somewhat independently. And we're sort of seeing, I would like to say we're seeing progression one way or the other, but I would say over the last year or so, what we're seeing is sort of changing between the buckets. So a year ago, we were seeing a lot of workflow chain type models. We see some amount of federated networks, but more recently, we're seeing more of a coordinator-based approach. And I think that speaks to the challenges of being able to actually observe and interpret the actions of an agentic system. And I'll talk a little bit more about that in a minute. So I'm going to talk now for the last 10 or so minutes about what does it mean to think about deploying and operating agents at what I call science scale. So trying to think about deploying large-scale scientific systems, agentic scientific systems that can operate autonomously for days or weeks using the resources that are available to us and hopefully lead to the types of results that large teams of researchers are currently working on. And so you can imagine that trying to deploy these agents at this sort of scale, there are several problems, right? We have large amounts of distributed specialized data, petabytes to exabytes of data that sits in these repositories. We have very unique laboratory instruments where we have everything from microscopes to telescopes, et cetera, that are deriving information. We have enormous high-performance computing systems. With that, many of these researchers have trained very specialized models and use sets of specialized tools for making particular calculations. And of course, importantly, and one thing that I think is becoming much more of a focal point of agentic systems is actually deploying these in a way that abides by the policies, the access controls, and the compliance requirements that are necessary. So I posit that agentic systems in the future are going to need to be scalable. They're going to need to be federated, and they're going to need to be infrastructure aware. And it may be because of my bias coming from the computer systems background. So in order to be able to realize these use cases, I think we're going to need a set of new scientific infrastructure that makes it easy for agents to authenticate, present identities, right? We're going to need identities for individual agents such that we can delegate authorizations to agents to perform specific roles, such that agents can communicate with each other easily and efficiently. I know chatting with Jay before this, we were talking about the inefficiencies of communication via natural language, right? There's going to need to be thoughts about how these agents can communicate more efficiently. We're going to need methods as we start having longer running agents with specialized capabilities for agents to discover each other, to be able to trust one another, right? You're going to want to use agents that have proven to be valuable in the past or have proven to be valuable to your colleagues before relying on the results they produce. We're going to need to, by definition, I believe, operate across facilities. Very little of the science I'm engaged with is conducted by one researcher in one laboratory or on one laptop. Mostly these researchers are teams of people with unique capabilities that are coming together and bringing together the various tools and instruments and computers in ways that are novel and interesting. And I think that same type of model is going to need to be applied to agentic systems. Importantly, we're going to need to be able to survive failures. So we need these agents to be persistent. We're going to need to be able to be dynamic, to move things around, and many, many other things. So as one way of thinking about this, our group has been focused on building what we call an agentic middleware. And so we have a framework called Academy, which is focused on really trying to provide a substrate and for deploying agents across this federated ecosystem of scientific infrastructure. We're focused on trying to build out simple agent abstractions. We're focused on very much on interoperating with the agent ecosystem. There is so much happening and so quickly, it's impossible, I think, my belief, for one group to be able to do everything. So there's just wonderful work with things like MCPs as a way of model context protocol, as a way of being able to invoke capabilities, skills for being able to encode experiences and ways of interacting with things, LangChain, et cetera, for being able to prompt and interpret responses from models. So when I say agentic middleware, what we're focused on here is producing a software layer that enables essentially management of the agent lifecycle, communication, coordination across distributed computing environments. And middleware, if you think from the distributed systems perspective, you can think almost like, how are we providing an operating system? How are we providing the services that these agents can exploit in their everyday activities? When you think about agentic middleware, there is such a broad range of challenges that need to be addressed, and this is sort of pointing to the fact that I think we need to all work together to be able to address these problems. So there's problems coming from, well, how do I interact with language models and prompt them and interpret responses? How do I enable agents to converse with one another? How do I efficiently call tools? What are the protocols that we should be using? From the low-level infrastructure side, there's problems of, well, how do I deploy agents in different places? How do I make them persistent? How do I present them with an identity and delegate authorizations? How do I enable these agents to perhaps move? And importantly, somewhere in the middle is, how do I observe these agentic systems? How do I gain trust in understanding what they've done? And so we like to think of it that Academy is coming from the left here, coming from the infrastructure up, and many of the other systems, LangChain, AutoGen, et cetera, are coming from the right, coming down. And hopefully we're going to meet somewhere in the middle to be able to realize these types of advanced federated deployments. So very quickly, the way we've thought about architecting Academy is it's an open source Python project. We've defined a simple scaffolding for an agent, where an agent has some set of actions that it can perform. It has that autonomous control loop, the policy that's driving it. It has a set of handles which enable it to communicate with other agents, humans, et cetera. And it has some state that's being acquired and learned over time. We've developed an interface essentially to launch these agents in different places. This is completely extensible, but the idea being that we should be able to tell an agent we would like to launch it in location X. That agent should be able to spin up and be able to then interact with other agents within its virtual organization of entities to which it can communicate. And then we need some way for these agents to actually communicate with one another. And we've adopted a very simple here asynchronous messaging model, where we basically define mailboxes that agents are associated with an agent and can be addressed. An agent can therefore send a message to another agent. It sits in a mailbox. When that agent is online or able to process message, it will retrieve the message, et cetera, et cetera. And that enables, we think, this sort of completely autonomous federated deployment of agents. So I'm just going to really quickly touch on a couple of problems that I think are critical to start thinking about. The first is observability. So I've mentioned this a couple of times. As we start deploying these systems more broadly at scale, we need to think a lot about how we trust what's coming out of them. Just as we trust, say, a microscope to provide an accurate image of a plant or a supercomputer to conduct a valid simulation, we need to be able to basically trust that our agents have performed the task that we ask them to perform in a reasonable manner. And this is work by colleagues at Oak Ridge and Argonne, Amal Garoji, Renan Souza, Rafael Ferreira da Silva, and they're really focused on observability and provenance. And they've thought about extending provenance standards to capture in a structured way information about what agentic systems are doing, right? What tools are being used, what reasoning process was being executed, et cetera, et cetera. And then they also have a framework called FlowCep that's providing a unified provenance collection framework that can sort of capture provenance information from the various frameworks and bring it together. We've been thinking a lot on our side about, well, how do I observe these federated agentic systems where these agents are running in different places? So this is a quick prototype UI built by someone in our team, Yadu Babuji. You can see here he's going to open up and look at an agentic system. He has 3 or 4 agents running. He can look at the logs, and you can see what these agents, you can see they're distributed in 3 or 4 data centers around the US. What he's going to do now is he's going to provide some human input, right? Because these agents often require interactions with humans. So we need a way for humans to engage when appropriate. And this provides an interface for those agents to interact with, for humans to interact with those systems. And you can see here he's just looking again at some of the logs so we can start understanding. So we're thinking that there's a lot of interesting questions to be asked about how do I understand what's happening, observe, interact with that system. And so now I'm just going to wrap up. So we wrote a paper a year or 2 ago now, published last year, about thinking about what would an agent-based scientific method look like. So I introduced the slide at the beginning, talking about the scientific life cycle from asking a question to proposing hypotheses to conducting experiments to publishing your results. And in this paper, it was a really interesting thought experiment to think about, well, what would happen if we replaced each of these steps with an agent or a set of agents that could perform particular tasks, like being able to generate testable hypotheses from knowledge that was extracted, being able to analyze data coming from simulations or experiments. And we think that there's an opportunity for these steps to be agentified in combination with sort of broad overarching agents that need to think about planning these activities, interpreting the trade-offs between how much resources are we investing in particular activities, enforcing the requirements in terms of safety and validity, being able to think about exploration, et cetera. So there's a lot of things to think about in that space, and we're seeing increasingly people implementing either parts of this loop or entirety of this loop using agentic systems. So just to summarize, so I think for many hundreds of years now, the pace of discovery really has been rate limited by the human, right? The human deciding what to do next, not based on the amount of data we have available or the computation, but really about how quickly we can compute that loop. So agents, particularly driven by these new capable language models, reasoning models, are giving, I guess, realizing some of that promise. These agents are acting as persistent, stateful processes that can act, adapt, and coordinate on our behalf. But I think there are a lot of open challenges. And I think from my perspective, one of the big things we're really focused on is I don't think we should be focused on removing scientists from the science, right? What we want to think about is how we remove scientists from the bits of the process that don't really require them, the mundane bits, the repetitive bits, the bits that require such enormous amounts of computation or data that's just infeasible for a human to actually understand. And enabling humans then to focus on the important bits, right? Like asking the right questions or interpreting the results, looking at the things that were unexpected, et cetera, et cetera. And I think from the systems perspective, there's a ton of really, really interesting infrastructure questions that we need to think about. Agents are going to fundamentally change the way we think about infrastructure. We've got to think in the near term that the primary user of our computing infrastructure is probably going to be agentic systems. And so what does that mean? We need things like federation. We need fault tolerance to support persistence. We need overarching identity, access management, authorization frameworks. We need ultimately observability and trust at some level of scale that we currently don't have. So with that, I'll say thank you. I should say a big acknowledgement to the Academy and the Globus teams, and particularly Ian Foster, from whom I borrowed several slides in this talk. So I'll turn it over to questions now, and thank you again for the opportunity. I really appreciate it.
Thank you, Kyle. Let's give Kyle some applause for that awesome presentation. I can't wait to make this available to many more people via our YouTube channel. We have a little bit of time for questions. And Kyle, if you have time, we're going to send you the questions we don't get to and start a new thing with the Google Cloud Advanced Computing community that I mentioned before the session. If you can just answer some of the additional ones or all, even verbally, we'll transcribe. We're going to post all the answers to the questions to today's session on our webpage for this event. Let's get into it. Alex Cheholko, sorry. In your experience, what are the most common and practical ways today to store the agent state? For example, MD files, SQLite, is it the same thing as memory?
Yeah, great question. That's probably the topic of the month at the moment, or maybe the topic of the last few months. So we're seeing a lot of people deploy saving state in MD files. We're seeing a lot of more in the science domain structured information being saved in traditional methods like relational databases. Obviously, at the scale of some of this, the science we're running, the state is really the outputs of these rather complex activities, which need to be saved in large files. How does this relate to memory? I think that's a really, really interesting question. So a lot of the focus in recent times has been on agentic memory, thinking about how do we group together memories in a way that they can be retrievable without overwhelming the context, right? We're already using a lot of tokens in all of our agentic systems and language models. So there's a really interesting sort of cost benefit analysis here of how do we store the important stuff? How do we think about it in tiers? How do we group the stuff such that we can index it very, very quickly? And there's a lot of work thinking about grouping sort of facts that have been determined over time, grouping them by temporally or topically, being able to synthesize them, being able to compress them such that we're only storing the sort of critical information that we want to get to later. So I think very, very related. I think both are very much open challenges and both very much relate to efficiency and how we're going to think about reducing costs, energy, et cetera.
All right. Next question from Macon Sao Faria. Is there a layer in the agents involved in these workflows that do any kind of high-level choices, something based on the literature and previous results, but bold, including guesses?
Yes. So that's a really big one. So a lot of people are building these like, obviously from the Google perspective, this co-scientist type architecture. I didn't talk too much about the co-scientist here, but the idea there is very much to think about how we mine literature, how we work out what's been done before, how we propose novel hypotheses, and this trade-off between the exploration and exploitation, right? So exploration being very broad, trying sort of more out there guesses maybe being not quite the right word, but more out there types of experiments versus sort of digging deep in a particular area. So there's a lot of literature in that space. I'd suggest taking a look at the co-scientist literature and having a look at how people are extending the co-scientist more broadly.
All right. Next question from Melyadri Chowdhury. Do you see the future of scientific AI being dominated by one general purpose agent that can handle an entire research workflow or by specialized agents collaborating?
Yeah. So that's a great question. So I am very biased on this answer. So I personally believe that it's not going to be efficient, cost effective to be able to have a monolith. I think at the moment, the way industry is going is very much monolith. So we are seeing these exceptionally capable, very large frontier models that can do sort of everything. My belief is that that's not sustainable from an energy cost perspective, and that having many more specialized models will be the future. I'm hopeful. I think that also is beneficial from the perspective of things like sovereignty, right? So we have specialized data that we want to keep to ourselves for various reasons, security, IP, national requirements, et cetera, et cetera. So my belief is that we're going to head towards this world of a lot more smaller, specialized models that will ultimately be more powerful and more cost effective. But this is tea leaf reading. Who knows what the future holds? And that's the exciting, I think, part of this area.
Great. Michael Weissner asks, agents are obviously important for the future, but given the risks emerging that agents don't follow guardrails well and can get hyper-fixated and pursue inappropriate solutions to achieve their goals, which will compound on longer runs, how can they be secured and monitored appropriately at scale?
Yeah, these questions, the exceptional question. This is another really, really hot topic. And we've seen a lot of that. So we've done a lot of experimentation with these long-running agentic systems, and we start to see things like certainly agents getting focused, hyper-focused in particular areas at the expense of potentially better solutions elsewhere. We see examples of agents become more serial. They have large computing capacity, parallel capacity available to them. They start off very broad, but ultimately devolve into very serial processing. So we're seeing a lot of unwanted behaviors that are happening there. In terms of particularly applications in biomedicine, genetics, et cetera, guardrails are so important, right? There's so many potentially undesirable behaviors that can be performed by these activities. I personally don't have an answer to this question, but I think it's just an area that a lot of people are focused on. A lot of the frontier labs are focused on. It's going to be an area that we need to think very deeply about to constrain the types of activities that can be done and ensure that these agents stay on target towards their objective. This is rapid fire of amazing questions.
Great answers too. You're really nailing the answers quickly as well. Rajat Roy asks, how do we ensure consensus between agents in a deployed system? In decisions, is there an arbiter?
That really comes down to the pattern. So we see both. I think for us as humans, I think it's easier to think about it in a very centralized manner, where we think about some arbiter that makes decisions, reviews potential candidates. We've done a lot of work recently. A couple of students in our group focused on sort of agent formation, and we've had agents playing essentially games that we believe mirror sort of scientific activities. So playing the game of Wordle is an interesting example because it's a large search space for which you get clues from experiments about results. And we've done a lot of experimenting there with sort of how can we craft teams? How often should these teams of agents communicate with each other? And we're seeing very interesting things to do with sort of this pairwise communication, obviously repetition of work versus a centralized controller that can be more efficient about these things. But the trade-off then comes up around sort of that exploration. So if I have lots of different agents operating more independently, I may get to more interesting, diverse results. Whereas if I force them to collaborate more, I may sort of end up with a mindset of the masses, right? So I think it very much is dependent on the type of activity you're trying to do, and there's no one-size-fits-all answer. But I do believe there's real opportunity around the specialization and sort of independent thinking.
There was a related question that I think you've largely answered, but you may want to expand on. It was, have you observed any cascading hallucinations amplified through multi-agent interactions within the loop? And what verification mechanisms or guardrails do you consider most effective to mitigate this issue?
Yeah, so that's a really good one. And it certainly happens. As soon as you've got many agents that are working together in some way, particularly you think, say the materials discovery one, if there's a moth structure that's not valid, that's being pushed through all the rest of the stages, we sort of end up with chaos and later agents trying to interpret these results. And one of the big problems we have is that it's quite hard to attribute fault in a multi-agent system, because if you're sort of assembling sort of opinions from many team members effectively to try and get to this result, trying to decompose, well, where did that exactly go wrong, is a really hard question to ask. There's a lot of work on this fault attribution stuff. There's some multi-agent benchmarks that have various activities, mostly industry-focused activities. You can start looking at how people are thinking about this, and there's work, trying to refresh my memory because one of our students was really looking at this. And there was a really strong correlation with sort of the ability to detect errors and the volume of the actual context. So almost, I think a lot of the signal comes from the fact there's a lot of context assembled across these agents. So if you sort of say, well, the bigger context is inevitably going to have a fault in it, that one's going to be wrong, that sort of ends up the way. And what we need to do is think, I think, more about how we can actually get to the specific parts, how we can trace that lineage to be able to identify the specific steps for which an error was injected, and then how that error propagated, amplified over time. But that's another, I mean, you guys are hitting all the open questions. These are, yeah.
All right, we've got time for one more before final announcements. And again, I want to encourage everybody to sign up for next week's session on quantum computing. I've got three of maybe the most I think I'll use the word fun for their conversational style. People in quantum computing, 3 thought leaders that are going to argue and debate and say some strong opinions next week. So I hope everybody will tune in for that. But let's do one more question for Kyle. We got a question here. Given the skepticism in traditional academia regarding reproducibility and interoperability in AI-driven data processing, what provenance tracking or verification mechanisms do you consider essential to meet rigorous scientific standards and build trust?
Yeah, so this really gets to I talked a little bit about the observability and provenance angle. And I think to some degree, we've sort of been relating this to, at some level, we already trust a lot of stuff we don't understand, right? I'm using simulation software I don't truly understand. I'm using microscopes I don't truly understand. And why am I doing that? I'm doing it because I trust the people that built it. These things have been verified independently and been shown to be performant and accurate. The community is relying on those layers. I think the same type of thing has to be applied to agentic systems. I think there's going to be layers of trust that we need to establish. It's infeasible for me if I were a biologist or materials scientist, to be able to trace all the lineage down to the deep technical details of what's been done. But perhaps I can start assuring myself of some of the outputs if I know that a particular agent has been performed really well before, has been validated independently, et cetera, et cetera. And then we need to turn to more of a test-driven type philosophy for how we interact with these systems. So that's another $1 million question, probably $1 billion question, starting to think about how we actually observe these systems at a level that we can instill the right level of trust to be able to build upon that work.
All right, great. Let's give Kyle another round of applause. That was a fantastic presentation and awesome Q&A as well, Kyle. That was great.